So today we'll be doing the derivative of x to the n with respect to x. And to start off, we will recall the limit definition of the derivative. So this is going to be the limit as h goes to 0 of x plus h to the n minus x to the n over h. And we use the fact that x plus h to the n is the sum from 0 to n of n choose k, x to the n minus k, h to the k. And when we expand that, we have x plus h to the n is n choose 0, x to the n plus n choose 1, x to the n minus 1 h plus n choose 2, x to the n minus 2 h squared, all the way up to n choose n, h to the n. And we'll also use the fact that n choose k is equal to n factorial over k factorial times n minus k factorial. And we will do this for n choose 0, n choose 1, n choose 2, and n choose n, just to see what the pattern looks like. So n choose 0, by definition, is n factorial over 0 factorial times n minus 0 factorial. So you have n factorial over, and 0 factorial is defined to be 1. So we have 1 times n factorial. These cancel, so we're left with 1 for n choose 1. So you have n factorial over 1 factorial times n minus 1 factorial. And we can rewrite n factorial as n times n minus 1 factorial. And 1 factorial is 1, and these cancel, so we're left with n. So now for n choose 2, something similar, we have n factorial over 2 factorial times n minus 2 factorial. And 2 factorial is 2. We can rewrite n factorial as n times n minus 1 times n minus 2 factorial divided by 2 times n minus 2 factorial. And the n minus 2 factorials cancel, and we're left with n times n minus 1 over 2. And lastly, for n choose n, we're left with n factorial over n factorial times n minus n factorial. So we're left with n factorial over n factorial times 0 factorial. And these cancel to 1, so we have 1 over 0 factorial, but we said 0 factorial is 1, so 1 over 1 is equal to 1. So with everything said and done, we have x plus h to the n. It should be x to the n plus nx to the n minus 1 h plus n times n minus 1 over 2 x to the n minus 2 h squared. And then we're just going to have h to the n. So we said that the derivative of x to the n. So before I proceed, all of these other terms would just be higher order powers of h. So h cubed, h to the 4th, and so on. And that would be useful for our purposes here. So this is equal to the limit as h goes to 0 of x plus h to the n minus x to the n all over h. So you have the limit as h goes to 0, and we'll just plug in x plus h to the n. So you have x to the n plus nx to the n minus 1h plus n times n minus 1 over 2 x to the n minus 2 h squared plus h to the n and minus x to the n times 1 over h. And as you can see, the x to the n's will end up canceling, and multiplying by that 1 over h term, we have the limit as h goes to 0. So we should have nx to the n minus 1 And we have plus n times n minus 1 over 2, x to the n minus 2, h plus all the way up to h to the n minus 1. And like I said previously, all of these are just higher order powers of h. So as the limit h goes to 0, we're going to have nx to the n minus 1 plus n times n minus 1 over 2, x to the n minus 2 times 0, plus, which is going to be 0, plus 0, plus 0, and then all the way up to 0 to the n minus 1 power, but that's also 0. And this cancels because it's multiplying by 0. So we're left with nx to the n minus 1 plus 0, which is just nx to the n minus 1. So now we can say that therefore, the derivative with respect to x of x to the n is equal to nx to the n minus 1. And that is exactly what we wanted to show.